Hello, and welcome to our discussion of complex limits and continuity. We begin with a topological concept, that is the complex and two-dimensional analog of open-bounded intervals in the real numbers. Let's take a fixed complex number z0 and a positive real number r. And then we'll define the open ball with center z0 and radius r to be the set B z0 semicolon r, which is the set of all complex numbers z, such that the modulus of z minus z0 is less than r. And here's the picture. I have, as usual when I'm drawing in the complex plane, labeled my x-axis as the reals, my imaginary axis, my y-axis as I times r. I have my center of the ball z0 here, that's a blue dot. I have the radius r, and I've drawn a dashed perimeter to the circle to indicate that it's open. So the open ball is all points z that are within a distance r of the number z0. And we will also work from time to time with the closed ball, and I'll denote that by b bar of z0r is going to be the set of all numbers z in the complex plane, such that the modulus of z minus z0 is less than or equal to r. So b bar allows the inequality to become an equality. For plain old b with the ball, it's a strict inequality. Modulus of z minus z0 is less than r. And if these sets look familiar, at least in terms of the picture, you've probably seen them in multivariable calculus, talking about open and closed balls in R2. That is exactly what they are here in the complex number c, because c is basically R2 when it's convenient for us. Please make sure you know this notation and this symbol mathfrak b of z0 semicolon r, because I will use this extensively in videos and in notes to come. Now with this notation, we can define the notion of a complex limit. Say we have a number L in the complex plane and a function f defined on the ball b of z0r, possibly not including the point z0. So f is defined for all complex numbers arbitrarily close to z0, but it doesn't have to be defined at z0. And then we say the limit as z goes to z0 of f of z equals L if for all epsilon greater than 0, there is a number delta greater than 0 such that if the modulus of z minus z0 is less than delta, then the modulus of f of z minus L is less than epsilon. So if you want the outputs f of z to be close to L, say within a distance epsilon of L, you need to take the inputs z to be close to z0, say within a distance of delta. In other words, this limit holds if whenever z is in the ball centered at z0 of radius delta, you have f of z in the ball centered at L of radius epsilon. And we will pretty much never work with this sort of epsilon delta analysis in this course. There may be one or two occasions, but the proofs will probably be optional arguments. Rather, you can just be content that all the familiar algebra of limits, and for that matter of continuity, will carry over from what you knew about real-valued functions or about functions taking values in Rn from multivariable calculus. Namely, you have things like the limit as z goes to z0 of f plus g is the limit as z goes to z0 of f plus the limit as z goes to z0 of g if both of these limits exist. And the same for multiplication by a constant number and for quotients and for all of those good algebraic properties. One thing that we do want to pay attention to is that limits pass through real and imaginary parts. And by that I mean you have the limit as z goes to z0 of f of z equals L if and only if two other limits hold. The limit as z goes to z0 of the real part of f of z equals the real part of L, and the limit as z goes to z0 of the imaginary part of f of z equals the imaginary part of L. If we think of complex numbers as ordered pairs in R2, the real and imaginary parts of a complex number are the x and y components of that ordered pair, and we know from multivariable calculus that you have a limit holding if and only if the limit holds in all the components of your vector. That's just what this if and only if with the real and imaginary parts is saying. Now, one of the challenges and one of the strengths of limits in the complex plane, just as in multivariable calculus, is that you can approach a point in the complex plane from many different paths. So say we take our point to be the origin here, denoted by the black dot at the intersection of the r and IR axes. If you want to consider the limit of a function approaching the origin, well, you'd have to consider it on this path, and this path, and this one, all your axes, but also this path, and this path, and this path, and this path. So the challenge is that if you want a limit to exist in the complex plane, you have to be assured that it exists no matter how you approach the point, and you can approach a point from many more directions in two-dimensional space than you can in one-dimensional space. Consequently, when a limit in the complex plane exists, various other properties of the function are often more robust or often stronger because you have to satisfy this multitude of directions of approach. Last, continuity, as we might expect. A function f defined on the ball centered at z0 of radius r is continuous at z0 if the limit as z goes to z0 of f of z equals f of z0. And here you note the function is defined on the whole ball, not just the ball minus the center, because you want to be able to plug in z0 to f. And for a counterexample, I claim the principal argument is discontinuous at all negative complex numbers, which is to say at all negative real numbers. So say we take a negative real number z, we'll write z as minus x for some positive number x. And let's think about the unit circle, or more precisely the circle of radius x. So I'm going to graph my point z equals minus x on the negative real axis. So r is my real axis, IR is my imaginary axis. And I'm going to approach this point in two different ways. Let's say I approach this point along this dashed blue path in the upper half plane. So if I start out in the positive real axis over on the right, and I go over to this point minus x, what's happening to the principal argument along this dashed blue line? Well, just think about the unit circle and how you rotate around it. This principal argument is going to approach pi, because to go from the positive real axis over to something on the negative real axis, you have to go from 0 radians over to pi radians in your angle. So along this dashed blue path, the principal argument approaches the number pi. But let's go another path. Let's go along the lower half plane. So we'll start from the positive real axis, and we'll go clockwise now along this dashed blue path. If I go along this dashed blue path, I will still reach minus x, but now the principal argument is going to approach minus pi. So we think we start on the positive real axis at 0 radians, we go clockwise along the dotted blue path, and when you go clockwise around the circle, your argument starts to approach minus pi as you get over to the negative real axis. So both the dashed blue path in the upper half plane and the dotted blue path in the lower half plane will take you to the number minus x and get you arbitrarily close to minus x, but the principal argument along the top path goes to pi, and the principal argument along the bottom path goes to minus pi. So you can approach the point minus x arbitrarily closely, and yet the principal argument doesn't have to take one value. It will take or approach two very distinct values, pi and minus pi. And we could come up with formulas for these circular paths, and we will do that in the near future, and show more precisely using some symbol pushing that principal argument approaches pi along one path and minus pi along the other path. But I think and I hope the picture makes this just as clear. So this is the power and the danger of taking limits in the complex plane. You have more directions of approach to a point, so it can be a lot harder for a limit to exist.